All right, I'm gonna go over this rotational kinetic energy worksheet. First of all, here's the equation: 1/2 IW squared, where I is the moment of inertia and W is the angular velocity. Should look like something you've seen before. It looks like the kinetic energy equation when there's linear motion, which is 1/2 mv squared. So this is what we call the rotational analog. When something is rolling, you've got to know it's got translational motion or translational kinetic energy and rotational kinetic energy. In other words, it moves two ways. When some basketball is rolling along the floor, it's rotating, and there's energy in that, and it's moving from one place to another place. That's called translational. Let's get a little definition over there. It's simply movement from one place to another. When something is moving, you have to know, well, rotating and moving from one place to another, it has two energies. So when something's rolling, it is and moving from one place to another, it has two energies. And, well, this will become important when we do this problem here. You've got an object, a cylinder, with the following mass and the following radius. It's at the top of an incline. What is the speed at the bottom of the incline? When there's no mention of something having speed, you assume that it has no speed. So it's at the top of an incline. It has mgh. And at the bottom, you've just learned that it has two kinds of Ke. It's got Ke rotational, and it's got Ke translational. It's moving from one place to another. So remember that. So we know that the total energy at the top, which is just mgh, equals the total energy at the bottom, which is the rotational kinetic energy, and the translational. So I'm going to clear this out here. Get rid of that. So what would the equation be? It would be, at the very beginning, it has mgh, and then it's got translational kinetic energy and rotational, which is I omega squared. But we were told that the moment of inertia was, it's a cylinder, so it's right over here. It's 1/2 mr squared. And now here's the big trick here. We're not going to substitute W because we'd like to get everything in terms of a linear variable. Instead, since W equals V over R, W squared is V squared over R squared. And that's really terrific because this cancels out, and we get the following equation. mgh is 1/2 mv squared plus 1/2 times 1/2 is 1/4 of v squared. And so m is in each term. Oops, I left out the m there. So let me just fix that. It's 1/4 nv squared. 1/4, because 1/2 times 1/2 mv squared, and all the m's cancel out, and we get gh equals 1/2 v squared plus 1/4 v squared. 1/2 plus 1/4, that's 2/4 plus 1/4. So gh equals 3/4 v squared. We want to find v, so we multiply both sides by 4/3. 4/3 gh, and v is radical 4/3 gh, and you substitute the g is 10, and the height is given as 0.67. So 4/3, 10 meters per second squared, times the height given as 0.67. That's meters, and you should get 3.0 meters per second is the v. Does the speed depend on the mass and the radius? Well, we canceled out the masses. It doesn't matter. And we also canceled out the radius. So we can see neither the mass nor the radius determine the speed. So the answer is no. It doesn't. Let's try another one. We've got two spheres. Here's the moment of inertia for the two spheres, 2/5 mr squared. They're going down an incline. One of them has a mass of 1.1, one of them with 0.18 radius. The other has a mass of 1.8 and 0.14. Which sphere gets to the bottom quicker? But we just learned that mass with these equations, when you have all potential energy at the top and at the bottom you have rotational and translational, the m's cancel out and the r's cancel out. So the answer, which sphere gets to the bottom quicker? How about we just write the same? They get to the bottom the same because the m and the r don't matter. So then the next question is, what is that velocity? All right, so we'll do it again. mgh equals 1/2. So at the top of the incline, it's only mgh. Then it's translational kinetic energy and rotational. So we're going to substitute in the moment of inertia that they gave us, which is plus, so it's 1/2 times the moment of inertia is 2/5 mr squared. That's what we were given. I'm not going to put w squared. I'm going to put v squared over r squared. And we get a nice little cancellation of the r squared. The masses also cancel out. So when we clean it up, we get GH is 1/2 v squared plus 1/2 times 2/5. That's 2/10. Yep, 2/10, which is of course 1/5. But m's cancel out, excuse me. R squared cancel out, so it's v squared. I have to add these two. So 1/2 is 5/10. 5/10 plus 2/10 is 7/10. So GH equals 5/10 and 2/10 is 7/10 v squared. Multiply by the reciprocal, you get 10/7 GH equals v squared, and v is radical 10/7 GH, and you substitute substitute 10, and h is given as, what's the height of this? 0.72, and you should get, when you take the square root of these three terms, 3.2 meters per second. Let's see, can we do the rest? Let's see. What is the rotational kinetic energy of a sphere with this mass and a radius of 0.085, rolling with an angular velocity of 5.2? Let's see what we got here. What's rotational kinetic energy? 1/2 I w squared. So 1/2 of the I. Well, we're told it's 2/5 mr squared times w squared. So that's a plug-in. So 1/2. So this 1/2 times 2/5 is 1/5. K times m, they gave us 0.82 kg, times the r, we're told is 0.058 meters. That r is squared. And then finally times w squared, which is 5.2 radians per second. That is squared, be careful. And the answer you should get is this. Okay, I think we'll do one more, finish the page. A mass of 0.36 radius. It's a hoop. That's got a big moment of inertia, rotating without slipping, moving linearly with an angular velocity of 4.8 radians per second. That's w. What's the total energy? Well, we know the total energy, maybe you call this KE total, equals the translational plus the rotational. So 1/2 m 0.36 kg times the v. Well, we're not given the v, so we're going to have to find it. You know that w is v over r, and so v is omega r. Omega is 4.8 radians per second, and the r given is 0.11 meters. Let's get out the calculator. So you get a v 0.528 meters per second, 0.528 meters per second, but be careful, that is squared. All right, 1/2 The moment of inertia is mr squared, so that's 0.36 kilograms times r squared, which is 0.11 meter squared, times the angular velocity they gave us, 4.8 radians per second, second squared. So if you do all the calculations, you get this answer right here, 0.10 joules. It's a little tough to see, that's a joule. 0.10 joules. And I think that's going to be it for this one.